Greetings, everyone. It's Professor Fiore. Today's topic is JFET Common Gate Lag Network Analysis. How's that for a mouthful? Basically, we want to find out what the high frequency performance is for a JFET Common Gate amplifier. In other words, one of these. So you might recall when we looked at common gate amplifiers in general, some of the characteristics are that it has a relatively low input impedance because you're driving the source of the FET rather than the gate. It has a non-inverting gain, so the drain signal is in phase with the input signal, and it's potentially a decently sized voltage gain. Because of the low input impedance that you're going to get looking into the source, this circuit tends to be pretty good as far as high frequency performance is concerned. Which, of course, is the topic of the day, right? So where do we begin? Well, first, we would like to get some idea of where this thing is biased. We're going to need to find values like the transconductance so that we can find the Zn over here. Also find the gain, things of that nature. So the very first thing to do would be to get some data on this device, a 5458. So you go hunting around and you might find something like this. So from Semi, from their data sheet, they give a range of IDSS that's from 2 to 9 milliamps, typically 6, and a GM0 that's 1.5 to 5.5 millisiemens, typically 4 millisiemens. So what I did is, instead of just shooting the middle here, is I went in and I looked at the TINA model, right? And that gives us essentially a GM0 value of 3.17 millisiemens and a VGS off value of negative 2.88 volts. Now, we can use these two values to calculate an IDSS value. Right? Remember, IDSS is the maximum current you're going to get. In other words, when VGS equals 0. So that's a negative GM0 VGS off divided by 2. Right? Usually we use the equation the other way around to find GM0, but I just manipulated this little algebra so we could find IDSS, which in this case is a little over 4.5 mils. Why did I want IDSS? Because ultimately I want to find the ID and GM values, and we're going to use a self-bias curve. Why am I using a self-bias curve? Because it's self-bias. So you notice right here at the source of the FET, there is this resistor RS going to ground. The gate of the FET is tied to ground. Consequently, the voltage across the gate source of the FET is the voltage across this resistor. And that's pretty much the definition of a self-bias, right? The current that flows through this resistor sets up a voltage, which is the bias voltage for the gate source. That's why it's called self-bias. If this is a little fuzzy, I suggest go back and look at some of the earlier JFET biasing videos. You can get a better idea of that, all right? But that's essentially what we're looking at. So let's continue along with our self-bias graph. So what we need is GM0 times RS on this axis. Remember, RS is the DC bias value. So we know the GM0 value, right? We know that's 3.17 millisiemens. So the DC bias value of RS is 2K, right? This right there. Remember, it's the DC value because we're looking at biasing. So you multiply those two up. 2K times 3.17 is going to give you 6.34. The millis and the Ks are going to cancel. So I go over here and find 6.34. So this is a logarithmic axis here, right? So that's 1, 2, 3, 4, 5, 6, and we're a little over 6, and we're around here somewhere. So on that light dotted line, which if you bring back, it's going to be about 0.18. So the ratio of ID to IDSS is about 0.18 or 18%. So if you want to find ID, right, you just take 18% of your IDSS. That works out to a little over 0.8 milliamps. I can also use my relation that the ratio of GM to GM0 is equal to the square root of ID over IDSS. So take the square root of your 0.18, multiply by your GM0, all right, and whoop, we get a GM. Right, so 0.42 times 3.17 millisiemens is 1.35 millisiemens. And that's really what I'm going to need for my future calculations. All right, so let's go back to our original circuit here. And as long as I know about where we're supposed to be, I can do some calculations. Like if I know I have a little over 0.8 mils coming down through here, that's going to give me, probably close to 5 volts across RD, which would imply, given a 15-volt power supply back here, that we should have about 10 volts at the drain, right? Drain to ground. And again, we should have maybe, 0.8 mils times the 2K. So that's going to be about 1.6, a little over 1.6 volts at the FET source. In other words, across this 2K. So let's do a little DC analysis just to make sure that we are, not flying off the handle. Okay, that what we have makes sense. All right, so let me grab node 5 here. So I'm getting 10.164, so just over 10 as we expected. Go to the source terminal, I'm getting 1.612. So again, just a little over the 1.6 we estimated. Looking pretty good. Now, from here, since we know the DC is working pretty good, we're pretty confident of this GM value being 1.35 millisiemens. Now we can start looking at the fun stuff for today, which is the lag network analysis. What does the equivalent circuit look like? All right, so let's go and look at this sort of redrawn. What we've done is basically taken the route we've taken in the other lag analysis videos. In other words, you take your coupling capacitors, right? These are a short for midband, so they're going to be short at any higher frequency. So you just short these out. And then your power supply, right? You just replace that with its ideal internal impedance. So that's a short to ground. In other words, the top end of RD goes to ground. So we're just going to draw this downward rather than upward because it looks kind of weird going up like this. So we're just going to draw it down here. The RD will be over here. All right, we have our source, the internal impedance of the generator at 50 ohms, and then we can actually look at the FET itself, right? What's inside the FET? And that's where we are here, right? So there's the RS, there's the RGen, there's the 6K that we had for the biasing resistor and a 12K load. Here is the model for the FET, all right? So obviously it's controlled current source, coming gate drain, and it's this polarity of current, right? Current is going left to right. If we have a positive to negative, in other words, out here on our gen to ground, if it's positive and negative, that's the direction of current flow we would get. So what we have in the source to gate position is the Z in source. Z in source, when we looked at common gate amplifiers, we figured that to be 1 over GM. We know GM is 1.35 millisiemens, just found that out a moment ago. So you divide that out and you get 741 ohms. All right, so I know that value now. The other question is, what do we have for the capacitors? All right, so when we look at this, remember there's 3 caps, right? Internal parasitic capacitors. There's basically one that goes from gate to source, there's one that goes from gate to drain, and there's one that goes from drain to source. The drain to source capacitance is usually small enough to ignore. So all we really have to worry about is the CGS and the CDG over here, right? CGS winds up being in parallel on the input, and C drain gate winds up being parallel on the output. There's, remember, no Miller effect here. Miller effect only occurs when you have an inverting amplifier. This is a non-inverting amplifier. So this is one of the reasons why we tend to have good high-frequency performance in these common gate amplifiers. All right, so we have the CGS and the CDG, which we can pull from a data sheet. All right, so they give us ranges, right? Remember, CRSS is the reverse capacitance that you would see in the measurement circuit. And they give us a typical value of 1.5 picofarads, 3 picofarads max. I'm going to use the typicals here. CISS, which is actually the combination of the reverse transfer capacitance, the CGD in other words, and the input capacitance, they're given 4.5 picofarads for that, 7 picofarads max. So I'm just, like I said, I'm just going to use the typicals here, right? So the drain gate basically is CRSS. So that, we're just going to take that as the given 1.5 picofarads. And then CGS, because CISS is really CGS plus CDG, we just subtract off that other piece and we get the value, right? So we get 4.5 minus 1.5, and that would be 3 picofarads typically. So that's what we're going to use. All right. Granted, this could be off a little bit. The manufacturer gives us a typical value, but that's not sort of written in stone, if you will. All right. But nonetheless, I have the capacitors and we can go about our merry business. Or non-merry business, as the case may be. So, what do we wind up with over here? All three of these resistors and capacitor, we wind up with something that's in parallel. Right? Notice we have all of these same connection points right here on this common node. Everything else goes to ground. Your VGen, you're going to replace that with its ideal internal impedance, which would be a short. So all the other runs go to ground. So everybody's essentially in parallel. So we're going to take the 741 and the 2K and the 50, and we're going to put them all in parallel. All right? Bingo. What's that going to be? Well, it's going to be a little less than 50 ohms. On the output end, we have our CDG of 1.5 picofarads, 6K and 12K. Put those in parallel. Well, that's a 2-to-1 ratio, so we're going to get 2/3 of this. All right, 2/3 of the smaller thing. That's 4K. So I got 4K for this, 1.5 pico for this. Certainly, that value is small enough we can ignore the internal impedance of the current source. If these were really, really big values, if they were 50, 100, 200 k ohms or something like that, this internal impedance would begin to impact. We'd start seeing several percent of shift just because of that. But this is large enough with these values that we can just ignore it, all right? So I now know the total resistance over here. That's 4K. I've got 1.5 picofarads for that. On the input end, we said we're going to get a little less than 50 ohms and 3 picofarads for that. So let's grind that through. And here we go. So on the input end, 3 picofarads, there's the 741 that we mentioned. Put these things in parallel with the 2K, that's 541 for your Z in. And your total value now, you put that in parallel with 50, you get 45.8. All right, so if you take 45.8, 3 picofarads, you run that through your universal critical frequency formula, 1/2 pi RC, and we get this amazingly large value of 1.16 gigahertz. Guess what? That's not real. When you have really small resistance values and really tiny capacitors, you can end up with calculated values that are actually well beyond the capability of the FET. Remember, we're dealing with a FET model here. So do I really think this FET could go out to, 1.1 gigahertz? No, I don't. Not for this little 5458, I don't. But nonetheless, as you're going to see, this is not a problem because we now move on to the output network. 1.5 picofarads. We took the 6 and the 12 in parallel and got 4. Use those two, we get 26.5 megahertz. So this is a more realistic number. And in fact, typically, unless you have some kind of odd circuit, this is closer to kind of the reality you're going to see. In other words, you might see a really small resistance capacitance out here producing this huge frequency on the input, but on the output, you see something a bit more modest, right? And really, all we care about is the dominant one. Ultimately, that's what's important. Which one affects mid-band response first? Well, this one, 26.5 megahertz, okay? Beauty. So let's go over to our circuit and do some analysis. Now, before I go any further, we could talk about the gain of this thing, because that's useful to know. So the gain would be the RD value, 6K and parallel 12K, right? So that would give us the AC value of drain or load, however you want to call that, which we know is 4K. And we're going to multiply that by the GM, which we know is 1.35 millisiemens. So that gives us a gain of about 5.4. Of course, of the input signal, not 100% of that's actually getting to the source. A little bit of that signal is going to be lost across the 50. Now, when you think of FET amplifiers, you tend to think, there's going to be no generator loss because the input impedance is so high. Well, that's true if you're driving the gate. In other words, if you have a common source or a common drain amplifier, but in a common gate, you're driving the source of the FET. So yeah, the input impedance is not that big, right? As we just saw, it's a little over 500 ohms. So you look at a 50 and a 500 for a Z-in, you're going to lose about 10% of the signal, right? So if you lose about 10% of the signal, your gain's 5.4. In other words, 5.4 times roughly 0.9, just estimating here. You're going to look at a gain that's 5-ish, maybe a little less. In any case, not to belabor the point over here, because, everybody wants to know what the results are. So let's do a little plot. We'll go from 1K up to 100 megahertz. See what we get. Okie dokie. So, nice flat response out to some higher frequency. Get our plotter on here. Move him out of the way. All right, so the mid-band gain that we're getting is 13.3 dB. So a gain of 5 would be 14 dB. So we were expecting just a smidge less than that, right? Like I said, 4.9 or something. So we're getting a little bit less, that would be, 13 point something dB if we did the conversion, but we're close, right? We're, within a reasonable range here. All right, so 13.3, now I have to find my 3 decibel down point for the system F2. So that's going to be 10.32 basically, right? 10.32 dB is what I'm looking for. It's going down, it's going down. There it goes. Oops, I think I just missed it. Back up one. Okay, right there. So we're looking at, well, depending on exactly where you go here, it's probably, like in between, whatever, close enough. Okay, let's call that 26.1 megahertz. All right. Okay, how did that compare? Where were we? Well, I just happened, big surprise, to copy some of this stuff down. All right, so here was the original calculations that we did. 26.5 megahertz. All right, okay. And our sim is coming in at 26.1, 26.5 versus 26.1. And we had, on the sim, we had, a smidge over 13.3 dB with the generator loss, right, versus our calculated, which was a little under 5, or about 13.9 dB. So looking pretty good, right? The obvious question is, how do I check the input lag, this supposed 1.16 gigahertz? Well, unfortunately, you don't, because there's no easy way to isolate this. When we do lead network analysis, it's pretty easy to just come in and change one of these caps, because it's the single cap that sets the critical frequency, in isolation, right? In association with the resistors, but one cap does it, and that cap doesn't change anything else. Doesn't change the bias, doesn't change the gain. In some cases, when we have let's say a common source amplifier, we can have a really big RGen back here, like 5K or something, and you can play with that, right? You could be 50 ohms, 500 ohms, 5K, whatever, and that's basically going to be the single element that affects the lag response. You can't really do that here. I could make RGen really big, but you're constrained by whatever the Z-in is. You can't get more resistance than that Z-in value, which, we already know is, somewhere in the, 500 ohm range, right? It was actually 541. So there's not a lot you can do there. But that's okay. Like I said, you're not going to get a performance, up in this range. You're not going to get 1,000 megahertz out of a little small signal FET like this, right? The important thing is that the typically dominant network, this is the output network, this comes out really nice, 26.1 megahertz versus 26.5. And again, don't forget, we're using manufacturer's typical values, okay, for our set up on those capacitors. What are they really? What are they going to be when you actually grab some in lab and throw them in a protoboard? Right, there is going to be a little bit of fuzz there, probably a lot more than what we're seeing between these two, right? Okay, great. That seemed to work out well. Any questions? Put them down in the comments, and we'll see you next time. Have a good one.